Today, we are exploring polar coordinates in further mathematics. In polar coordinates, a point is described in two parts. The first part is the distance from the origin, which we call r. The second part is the angle turned from a fixed direction, which we call theta. There is also a formula for finding the area of a wedge-shaped region traced out by a polar curve. In plain words, the area is 1/2 of r squared, integrated with respect to theta. In symbols, that is, area equals 1/2 times the integral of r squared d theta. Let us begin with a worked example, converting a polar point into Cartesian coordinates. Suppose our point has r equal to 4 and theta equal to pi/3. To find the x-coordinate, we use the rule x equals r times cosine of theta. Substituting our values, x equals 4 times cosine of pi/3, which equals 4 times 1/2, giving x equals 2. To find the y-coordinate, we use the rule y equals r times sine of theta. Substituting our values, y equals 4 times sin of pi/3, which equals 4 times √3/2, giving y equals 2 √3. So our point in Cartesian coordinates is 2, 2 √3. On screen, we show this point first as a flat two-dimensional dot on the polar grid at radius 4 and angle pi/3. Then we rotate the view into 3 dimensions, lifting the same point up so you can see how the radius and angle sit inside a fuller picture of the plane. Now let us find the area of a polar wedge, using the curve where r stays constant at 4, swept from theta equals 0 to theta equals pi/3. We begin with the area formula, area equals 1/2 times the integral from 0 to pi/3 of r squared d theta. Substituting r equals 4, we get area equals 1/2 times the integral from 0 to pi/3 of 16 d theta. Integrating 16 with respect to theta gives 16 theta. Multiplying by the 1/2 out front gives 8 theta, evaluated from 0 to pi/3. Substituting the upper limit, 8 times pi/3 minus 8 times 0 gives an area of 8 pi/3. On screen, we show this wedge as a flat two-dimensional slice of a circle, like a slice of pie shaded in. Then we transform the same shape into 3 dimensions, tilting it so you can see it as a slice of a cone standing on the circle of radius 4. For our check step, we compare this to the ordinary sector area formula, which is theta divided by 2 pi times pi r squared. Substituting our values, the quantity pi/3 divided by 2 pi times 16 also gives 8 pi/3. Since both methods agree, and the area is a positive number that matches a small 60-degree slice of a circle of radius 4, our answer is confirmed correct. This shows how polar coordinates let us describe points and regions using distance and angle, and how the wedge area formula connects neatly back to familiar circle geometry.